Hello everyone, welcome to my YouTube channel Techno E-Learnings. In this tutorial, I'm going to discuss about NAND and NOR, the universal logic gates. Universal logic gates, that is NAND and NOR, are basic building blocks in digital electronic circuits, using which any other logic gates like NOT, AND, OR, XOR, etc. can be implemented without requiring other types. Digital circuits implemented using universal logic gates simplifies the circuit complexity and improves the efficiency of the circuit. These universal logic gates can be combined to form any required digital circuits. Implementing digital circuits using universal logic gates reduces the number of gate types required in a circuit. Using a single type of gate can be more efficient in terms of manufacturing and design. Let's start with laws of Boolean algebra. Boolean algebra provides the mathematical foundation for digital electronics, logic design, and computer programming using operators like AND, OR, NOT to simplify complex logic expressions and circuits. The laws of Boolean algebra is given in table below. Implementation of basic logic gates using NAND gate. A NAND gate is a digital logic circuit that produces a logic low output only when all its inputs are logic high. The symbol of a two-input NAND gate along with its truth table is shown in figure 1. NOT gate. The symbol and the truth table of a NOT gate is shown in figure 2. Here A represents the input signal and Y is the output signal. In the truth table, output Y, which is equals to A bar, indicates that Y is inverse or complement of input A. Not logic using NAND gate. As shown in the truth table of the NAND gate, if A and B are 0, Y equals to 1. And if A and B are equals to 1, Y equals to 0. This means if both inputs of the NAND gate are same, then the NAND gate will behave like a NOT gate. Therefore, to realize NOT logic using a NAND gate, both the inputs of the NAND gate are sorted together as shown in figure 3. This gives an output Y, which is complement of input A. AND gate. The symbol and the truth table of an AND gate is shown in figure 4. As shown below, in the AND operation, when both inputs A and B are logic 1, output Y is also logic 1. For other combinations of the inputs, the output Y equals to 0. The output Y in the truth table of the AND gate shows that it is just complement of the NAND gate for the same combinations of inputs A and B. AND logic using NAND gates. So to realize an AND logic using NAND gates, the output of the NAND gate needs to be inverted. Figure 5 shows the AND logic realization using NAND gates, where the output of NAND 1 is Y1 equals to A dot B bar. This is then inverted using NAND 2 to produce Y equals to A dot B, which is same as that of an AND gate. OR gate. The symbol and the truth table of an OR gate is shown in figure 6. In this OR operation, when both inputs A and B are logic 0, output Y is also logic 0. For other combinations of the inputs, the output Y equals to 1. OR logic using NAND gates. The implementation of the OR logic using NAND gate is shown in figure 7. Both NAND 1 and NAND 2 behaves like NOT gate. The output of NAND 1 and NAND 2 are as given below. Y1 equals to A bar and Y2 equals to B bar. The NAND 3 output Y3, which is same as Y, is then computed using Y1 and Y2 as inputs to get the OR logic. This relation is based upon the De Morgan's law and double complementation law. Y equals to Y3 equals to Y1 dot Y2 whole bar equals to A bar dot B bar whole bar equals to A plus B double bar equals to A plus B. NOR gate. The symbol and the truth table of a NOR gate is shown in figure 8. NOR gate produces a logic high output only when all its inputs are logic low. NOR logic is simply the inverted or complemented version of the OR logic as shown below. Y equals to A plus B whole bar. NOR logic using NAND gates. To implement the NOR logic using NAND gates, the OR logic realized using NAND gates has to be inverted one more time as shown in figure 9. XOR gate. The symbol and the truth table of an XOR gate is shown in figure 10. The output Y of this XOR gate is logic 0 when both inputs A and B are same, else Y equals to 1. As shown in the truth table above, the output Y of the XOR gate is logic 1 only when A equals to 0 and B equals to 1 or A equals to 1 and b equals to 0. Using Boolean algebra, this condition can be expressed as y equals to a bar dot b plus a dot b bar, which is equals to a XOR b. XOR logic using NAND gates. The implementation of XOR logic using only NAND gates is shown in figure 11. The output of the NAND 1, that is y1 equals to a dot b bar. Now the outputs of NAND 2 and NAND 3 are computed as y2 equals to a dot b bar whole bar and y3 equals to b dot a dot b bar whole bar. Outputs y2 and y3 are used as inputs to NAND 4. The output of NAND 4 is computed as y, which is equals to y4, is equals to a dot b bar whole bar dot b dot a dot b bar whole bar whole bar. In order to get the expression for XOR logic, the output y is further simplified using Boolean algebra as shown in the table. Implementation of basic logic gates using NOR gate. A NOR gate is a digital logic circuit that produces a logic high output only when all its inputs are logic low. The symbol and the truth table of a two-input NOR gate is shown in figure 12. Not logic using NOR gate. As shown in the truth table of the NOR gate, if A equals to B equals to 0, Y equals to 1. And if A equals to B equals to 1, Y equals to 0. This means if both the inputs of the NOR gate are same, then the NOR gate will behave like a NOT gate. Therefore, to realize NOT logic using a NOR gate, both the inputs of the NOR gate are sorted together as shown in figure 13. This gives an output Y, which is complement of input A. OR logic using NOR gates. Since the OR gate is the inverse of the NOR gate, complementing the output of a NOR gate using a NOT gate will give the result of an OR gate. The implementation of an OR gate using NOR gates is shown in figure 14. AND logic using NOR gates. The implementation of the AND logic using NOR gates is shown in figure 15. Both NOR1 and NOR2 behaves like NOT gate. The outputs of NOR1 and NOR2 are as given below. Y1 equals to A bar and Y2 equals to B bar. The NOR3 output Y3, which is same as Y, is then computed using Y1 and Y2 as inputs to get the AND logic. This realization is based upon the De Morgan's law and double complementation law. Here Y equals to Y1 plus Y2 whole bar equals to A bar plus B bar whole bar equals to A dot B double bar, which is equals to A dot B. NAND logic using NOR gates. Since the NAND gate is the complement of the AND gate, the implementation of the NAND gate using NOR gates is shown in figure 16. NOR 4 gate, in which both the inputs are sorted, is used to invert the output Y3, which is equals to A dot B, to produce Y equals to A dot B bar. XOR logic using NOR gates. The implementation of XOR logic using NOR gates is shown in figure 17. To understand the implementation, the output of each stage needs to be analyzed. The outputs at y1, y2 and y3 are expressed as y1 equals to a plus b whole bar, y2 equals to a plus b bar whole bar and y3 equals to b plus a plus b bar whole bar. The output at y4 is y4 equals to a plus b bar whole bar plus b plus a plus b bar whole bar whole bar. To simplify the output y4, laws of Boolean algebra are used. The final output obtained at y4 is as given in table below. So, the final result shows that this is nothing but the XNOR logic function. To get the final output y, the logic can further be simplified as given below. As shown above, the expression of the output y is the XOR logic which is obtained using NOR gates. Conclusions. Both NAND and NOR gates are known as universal logic gates because any Boolean function can be implemented using either NAND gates or NOR gates. Implementing digital circuits using universal logic gates reduce the number of gate types required in a circuit. Using a single type of gate can be more efficient in terms of manufacturing and design. Laws of Boolean algebra are used to simplify the logic expressions in order to implement and analyze the complex logic circuits.
Thank you for watching this tutorial.